This is the last few parts of integration. We've done lots before on products and quotients that we use substitution and just standard integrals as well. We're going to pull it all together and we need to use integration by parts. This formula is given to you in the booklet, and if you think about the product rule for differentiation from C3, it's leave the second, differentiate the first, this part here, plus leave the first, differentiate the second. If we rearrange it, we get u dv by dx equals d by dx of uv, and so on. Now what we can do is integrate, so integrate each term with respect to x gives us the integral of u dv by dx, and the dx part is with respect to x, and then d by dx of uv with respect to x, and then integrate the last part, du by dx, the dx. And what we'll see here is that this part here can actually be simplified, because since differentiating a function and then integrating it, it leaves it absolutely unchanged. So this part here can actually just be uv, and that gives us the formula at the bottom, this one here. Now this is integration by parts, and this is actually given to you in the formula booklet. So what's it actually saying? We've got, at this point here, we have a product, and the products that we've seen before is one is a derivative of the other, or we can use substitution. But integration by parts allows us to integrate when we've got a product or even a quotient and make it into a product, and from there we can, there's no connection between them, so therefore we can integrate the whole product. The thing to look for is this is u at this side, so we choose part of the product that can be differentiated, so there's your differentiation part, and this part here we assume it's already been differentiated and we integrate it to get v. So usually if we've got a power, we choose the power one, so say it was x squared, we would choose it to be u so that we can differentiate it, and then the other part would be the part to integrate. So first part, choose to differentiate, second part of the product, choose to integrate. And we can do a few examples on this to show you how it works. So example 16, we have got a product here, and as you can see there's no connection. If we differentiate the x, we get 1, which is not connected to cos x. If we differentiate or integrate cos x, there's no connection there with x. So this is what we do then. We choose a u and our dv by dx from our product at the beginning. So our u is going to be x and our dv by dx is going to be cos x. So we need, from our formula, we need du by dx, which is simply going to be 1, and if we integrate cos, we get sine. So that gives us the 4 components that we need for our integration by parts. We quote the formula, which is the integral of u dv by dx with respect to x is equal to u times v minus the integral of v du by dx with respect to x. And what we're actually hoping to do here is we've got a product which we can't integrate as such using the techniques that we've had before, but if we apply integration by parts, this integral should actually be simpler, and you can see there that du by dx is 1, so we're actually going to get much simpler integration to do here. So we will have our u was x and our v was sine x. So we take these two together and that becomes our first part. So x sine x minus the integral, and v was sine x, and that was all multiplied by the du, which is just 1 with respect to x. So you can see here that that is actually going to be so much simpler. So we get x sine x, and when we integrate sine, we get minus cos, so it's minus cos of x, and obviously with your plus c. So altogether we get x sine x, double negative gives us a plus, and cos x plus c. Remember, if you wanted to do your sine cos, sine cos, sine cos, plus plus, minus minus, plus plus, so going from plus sine, we're going upwards for integration, plus sine goes to minus cos. So that would be our answer for that. Don't forget your plus c, because it's an indefinite integral. Moving on to our next example. This is a very special case. Now it's special because we cannot choose ln to integrate. We just can't. So it seems against the grain, because we'd usually choose the x squared as u so that we can differentiate it and reduce the power. But this is not the case. This is a very special case, and we have to actually choose this one to differentiate. So choose the ln x to be differentiated. So that there is going to be our dv by dx, so we're going to integrate that, and that one there is actually going to be our u. We apply our formula again, and we're going to choose our u to be ln x, and our dv by dx is equal to x squared. So if we differentiate ln, we get 1 over x, and if we integrate our x squared, we get x cubed over 3. But you'll see this will work out quite well, because we get a bit of cancelling when we come back to this integral here. It'll actually help us, because we'll be able to do some simplification with the algebra. Should be a dx on there. Right, let's substitute in everything that we've got then. Our u is ln x and our v is x cubed. So I'm going to put it in that order. It's a bit easier to write. Minus the integral of x cubed over 3, and du by dx is 1 over x. So you can see there that this integral we will be able to cancel the x's down here, and it'll make it so much easier to do that. So that's why it's a special case. So just remember, if you see ln, one that's really quite popular is just the integration of ln itself, and we have to make it into a product of 1 times it. So that should work out. So let's calculate this. So the first part doesn't change at all. And then we've got minus the integral, and if we tidy this up, we get x squared over 3 with integrate with respect to x. So our final answer is add 1 to the power, divide through by the new power, and then our constant of integration. So we can say that our original x squared ln x dx is that integral. Right, we might actually get one that's a little bit more complicated. And this is where we have to actually apply integration by parts twice. Now, the reason being is if we look at the x squared, if we choose this to differentiate, which we're going to do, it reduces the power, but it goes to 2x. So if you think about the right hand side, the integral is simplified, but we still have to integrate again. If we'd had x cubed, e to the x, we'd have to do it 3 times and so on. So we're going to choose our x squared as u, and we're going to choose the e to the x as dv by dx. So that's the one that we're actually going to integrate. With e to the x, if you integrate it or differentiate it, you get the same e to the x as the answer. So we will get an integral, and hopefully it will simplify a little bit more. So first time round then, we have u is equal to x squared. That means du by dx is equal to 2x. We've got dv by dx, so that's e to the x, and to get v we integrate, which is e to the x. If we now substitute that into our integration by parts formula, we get x squared e to the x minus the integral of v, which is e to the x, and du by dx is 2x. I'll just put it at the beginning, it's a bit easier to see, so with respect. So what you can see again here is that we've got an integral, which is great, but if you look again, we're going to have to apply integration by parts again, because although we've reduced the original integral, then we've got one that's a little bit more complicated. So we'll take this again then, and we'll take it separately at the side, and we've got the integral of 2x e to the x. If we apply integration by parts on this, so we'll let u equal the 2x. That means du by dx we differentiate as 2. If we take dv by dx to be e to the x, then v is equal to, integrate that as e to the x. So it should work out a little bit better. So if we take the original, x squared e to the x minus, and then I'm going to apply by parts on here, so it's u times v, so that's changed to 2x e to the x, minus, now the integral is going to be simpler again, and that's going to be v times du by dx from the blue part. So v is e to the x, so it's going to become 2e to the x dx. And you can see there, that's quite a bit simpler. Okay, so we get x squared e to the x from the original, minus 2x e to the x, which was from the second integral, and then I've got a minus minus, so that's going to turn into a plus 2e to the x, and then plus the constant of integration. So this is where, because we had this x squared up here, we had to apply integration by parts, but then integration by parts a second time to do that. And as I said before, if that x squared had been x cubed, we'd have to do it 3 times. Right, an example is what I briefly spoke about when we were doing integration by parts with a product and ln. Natural log of x we cannot integrate, so we've got to do something really special here, and we've got to introduce a product. Now if we multiply by 1, we've not actually changed it, so I'm going to change it into the integral, which is the same as between the limits 1 and 2, and it's 1 multiplied, the dot just means multiplied by ln x dx. And what we've got is a product, but it allows us, if you think from before, it allows us to integrate this, but differentiate this one. So if we take this first one to be our dv by dx and this one to be our u, then we can do our integration by parts and also put in our limits. So this time we're doing a definite integral. And if you notice here, it says your answer in terms of natural logarithms. So we want an exact answer here. We have the formula. So this is your integration by parts. Remember, it's given to you in the formula booklet. We can't integrate ln, so we introduce 1 times ln. 1 is what we choose to integrate, so we're choosing this one to integrate, and we're choosing ln to differentiate. So u is equal to ln x. That means that du by dx is equal to 1 over x. dv by dx is equal to 1, so v is equal to x. We're going to pop these values into our integration by parts. So u times v is x ln x minus, now we've got it going from 1 to 2, so we've got a definite integral from 1 to 2, and v is x, and du by dx is 1 over x dx. So that's simplified our integral again, because we can actually cancel these x's out, and it makes it much simpler. So we also have to put this in terms of the boundaries, upper and lower boundaries. So I should really put on this part here a square brackets, one between 1 and 2. So we get x ln x in between 1 and 2 minus the integral of 1 dx. Simplify that, we get x ln x in between 1 and 2 minus, and that becomes x in between 1 and 2. Pop your substitutions in, and we get 2 natural log 2 minus 1 natural log 1, and then from this part we get 2 minus 1, and then our final answer is going to be, now remembering from your natural logarithms, ln of 1 is 0, so that goes out altogether. So we're left with 2 ln 2 and minus 1. We could also write that, the answer, it might say in terms of natural log 4, so it could be ln 4 minus 1. And that's what we have to do when we have a definite integral. So what I'd like you to do now is turn over to the next page. There is exercise 6G. If you look at the top here, you've been given the following integrals, should be given in the formula booklet, but you can verify them, but we're going to use some of these in the next exercise. So what I'd like you to do is question 1, A, B and D. Then moving on, question 2, A, D and C. Question 3, the first part, and then question 4, A and B. So if you stop the video just now, give yourself about 10 minutes to do those ones, practicing integration by parts, and then question 4 follows on from the very last example. Welcome back, and here are some of the solutions for you. Looking at question 1, you can pause this video to have a look at them, and I'll move on with some of the answers. And then looking at question 2, the ones that I've asked you to do are actually the bare minimum, so if you can do a little bit more for practice, then that would be great. That's the solutions for question 2. Then moving on to the next page, we've got last part of 2, if you manage to do any of those ones as extra. Question 3. And then we've got the remainder of 3, then question 4. Move that up. Check your answers on those ones as well. Right, the next part, oh, we've still got question 4 on there. I'll move that up. Right, the next part is we're actually going to revisit what we did in C2, so it's the Trapezium Rule. And if you look in the C2 section, you will find this formula in your formula booklet. And it was adding up, it's called the Trapezium Rule because we add strips of trapezia together to give you an area. It's an approximate value for a definite integral. And what we'll look at in example 20 is the sec graph, and in between 0 and pi by 3. So I've done a little sketch of this on Desmos, if you like to do a little sketch, and then you can see that we want the exact integral, and then we want 2 strips and then 4 strips. So I've done the diagram for the last part of the example, and then we can look at the percentage error as well, which can sometimes be asked for. So we want the integral for sec x first of all, and if we go back to just before exercise 6G, if you look on that page, you'll see that it's a standard integral and it's ln of the modulus of sec x plus tan x. That's what we're going to use in between the values, the limits of 0 and pi by 3. So for part A, we've got the integral between 0 and pi by 3 of sec x dx. Now if we integrate sec, as we said before, it becomes ln of sec x plus tan x. That's the modulus of it, remember, because we can't take the log of a negative number, and that's in between 0 and pi by 3. If we then substitute in our upper limit and lower limit, we get, now it's, sec is 1 over cos, so if we work that out, sec of pi by 3 is actually equal to 1 over cos of pi by 3, which is 1 over 0.5, which is actually equal to 2, and so on. And then the tan of pi by 3 is root 3. So for the first section for pi by 3, we're going to get ln of 2 plus root 3. And then the second part, we're going to get ln of, now the sec of 0 is 1 over the cos of 0, so that's going to be 1, and then plus 0. If we calculate that, we get just ln of 2 plus root 3. And the reason for that, remember, is if you get ln of 1, it's just equal to 0. So that's your first part. Right, second part, we want 2 strips. So if we've only got 2 strips, it's going to go between 0, pi by 6 and pi by 3. So we need to get our ordinates for these ones. So it's going to be 1, whatever that value is, and 2 for that one. So if we do a little table, as we'd have done before for C2. So we take our x values of 0, pi by 6, and pi by 3. This should just be revision for you. We get our ordinates, or our y value, that's 1, 1.155, and 2. If we then pop it into our formula for the trapezium rule, then the integral that we've got from 0 to pi by 3 for sec x for 2 strips is going to be approximately equal to a half of the width of each strip, which is pi by 6, the first plus the last, plus 2 times the middle. And that works out to be approximately 1.390 and so on, but we'll give our answer to 3 significant figures, so 1.39 to 3 significant figures. Now, in the same way, I want to do exactly the same with 4 strips. So you can see from the diagram here, the 4 strips that we've got allows us to have 0, pi by 2, pi by 12 rather, pi by 6, pi by 4 and pi by 3, so that's your x values, and then we want the corresponding y0, y1, y2, y3 and y4. So our first and our last and twice the middles. Now let's work this out then. So for this one, for part C, we've got our x values and we've got a corresponding y ordinate values. So 0, pi by 12, pi by 6, pi by 4 and pi by 3. Then it's 1, 1.035, 1.155. Make sure you can do this on your calculator, please. 414 and 2. So it's using your sec, but it's 1 over cos function. So the integral is going to be, the area is approximately going to be equal to a half of each of the strip widths, which is pi by 12, multiplied by the first ordinate, which is 1, the last one, which is 2, and then add on twice the middles. And that works out to be pi by 24 multiplied by 10.208, and that works out to be 1.336224.075, and we'll take that to 1.34, so it's 3 significant figures. If it doesn't say in the question, then please use 3 significant figures. Part D is asking for the percentage error using B. So percentage error, which you sometimes is asked for, it's not that common. It's 1.390 and all the rest of it. Take away the actual area. Because if you see from the diagram, it's going to be the approximation is an overestimate, and that's divided by the actual area that we calculated. We multiply it by 100 and we should get 5.6%. So that's the percentage error if we're using B. So that's using B. If we want to use C, we've used more strips. So we're expecting, it's still going to be an overestimate, but we're still expecting a percentage error, but hopefully that error is going to be a little bit smaller. So the area that we worked out in, so that what I'm doing here is using C. I'm taking the area that we worked out for that one, take away the actual area, so that'll give us the difference that it's over, so an overestimate, and then from there divide by the actual area that we got, multiply it by 100 to convert it, and indeed that's much smaller, it's 1.5%. So more strips i.e. part C is more accurate. And as I say, the trapezium rule does get asked for as well as a definite integral. This part D, it sometimes gets asked for, but not very often. Right, what I'd like you to do now then is exercise 6H. We're looking at questions 1, A, B and C. Question 2. And if you stop the video, give yourself about 10 minutes to do those, and then we'll reveal the answer. Welcome back. Here are the answers. So A, C and E. It's A, C and E. Then we go on to the next question, question 2. We have to do integration by parts on that one. So we're working out the exact area and then by parts, and then finding the percentage error, just like in the example. And then on to question 4. That was finding the exact value from 0 to 2. And that was by substitution rather than by parts. We can now use integration. Oh, I've got some more answers here which I didn't do. If you want to go on and do some more of the exercise, then that's absolutely fantastic. Just keep on going. I've put in all the answers here for the exercise. Oh, I think that's all. What question that is. What's the next part? Okay. So I still think that's question 4. That's the second part of it. Okay, so we're now going to work out areas and volumes. These formulae are not given, so you have to memorise them. So the area between a region, that's just C2 work that you've done before. So this here, that's done in C2. This is the one that is different. So if it's rotated about the y-axis, you actually get a volume. And this is not given, but if you can imagine, we are rotating it about the axis, so we're doing some sort of circular measure in angles. So just as we've done before, if it's any trig functions, we work in pi and radians. So the volume is pi between the limits of a and b and y squared dx. So it has to be y squared. Right, first example then, we have the region R is bounded by the curve with equation y equals sine 2x, the x-axis, and these lines. Find the area. Now it might be quite useful to do a little bit of a diagram here. So if we do a little bit of a sketch of what this looks like, give a better idea. So it's sine 2x and there's twice as many going to be in there for this one, so this is starting at 0. So this is going to be at pi by 2, up to there is pi by 4, and it's going to have a maximum at 1. That's what it's going to look like. So first of all we want to find out the area. So for part A, which is in between 0 and pi by 2 of sine 2x dx. So we've done that before, that's really straightforward hopefully. Now we're integrating, so sine goes to minus cos 2x, Then we've got the chain rule happening here, so we've got to go back and divide by the 2, so we get half. And that's in between 0 and pi by 2. If we put those values in, remember working in radians, we get minus a half times minus 1, and then take away minus a half. And that gives us an answer of 1. Now what we're going to look at now is the volume, and what you've got to imagine is taking this area and rotating it about the x-axis. And if you do that, you get a sort of a disc, a 3D disc that comes round, and we get a full volume for that. So what's that going to look like then? Well, if we put it into the formula that we've got, it states that it's pi in between a and b, which is 0 and pi by 2, of y squared dx. So that then becomes pi of 0 to pi by 2 of y squared is sine squared 2x dx. Now as soon as you see sine squared, you're going to have to use the double angle formula. So if I use cos of 4x is equal to 1 minus 2 sine squared 2x, and if I rearrange that, that gives me sine squared, so rearrange it to get sine squared 2x, so I can pop that back into the integral, and it makes us able to do that. So same sort of thing again, when you've got sine squared or cos squared, you revert to the double angle formula to help you out. So that's going to give me pi 0 to pi by 2, and that's going to change into a half of 1 minus cos 4x dx. Right, I'm going to tidy this up a little bit. So I've got pi outside, then if we put in pi by, it would help if I actually integrated it first of all, wouldn't it? So I'll take the half out, and then that's actually going to be x minus a quarter sine 4x, and that's in between 0 and pi by 2. So we pop our limits in, altogether we'll get pi squared upon 4 minus 0, and minus 0 as well when we put the 0 in, so altogether that's going to be pi squared upon 4. So that's the volume, so that's going to be units cubed, and our previous one was units squared. So that's what we're looking at when we want to do volumes. Right, moving on to another example, which is a parametric one, and sometimes you are given parameters, so it becomes very synoptic with what we've done before in terms of C3. So when we're the area and the volume, we've got formulae for that as well. So if we look for the area, and this is something that's not given to you, so you have to memorise that. So for the area, when we've got parametric, you've come across this before, it's the integral of y dx by dt times dt. And then if we come across the volume, we're going to use pi times the integral of y squared dx by dt dt. And all we're doing here is we're using the chain rule to get our dx, because we're working in terms of parameter, which is t, so it should actually work out okay here. So as soon as we see parametric, that's the area and the volume formulae that's not given to us, so we have to actually remember how to do that, and it helps if you remember the chain rule here. So getting back to the equation then, the question in part A, find the exact area of R. So the area is going to be from 0 to 2 of y dx, but then we've got to change that. So our limits are for x, but we want to change it to t, simply because it's with respect to t. So we're now going to use the integral of y dx by dt. So we've got y is equal to 1 over 1 plus t, but our x is equal to t plus t squared, so we need dx by dt, which is 1 plus 2t. So if we put that in now, but then we've got to change the limits as well. So when x is equal to 0, then that means that t 1 plus t is equal to 0. So t is equal to 0 or minus 1. But we're told, if you look in the question, we're told that t is greater than 0. So we're going to take on the value of 0 there. So that becomes 0. And then when x is equal to 2, we get a little quadratic. So we get t1 plus t is equal to 2. Rearrange that to get a quadratic of t squared plus t minus 2 equals 0. Factorise that, and we get t plus 2, t minus 1. So t is equal to, has to be 1 because t is greater or equal to 0. Right, so it's going from 0 to 1. Right, let's start putting in all the bits and pieces. So we have, move this up a little bit. We have the area is equal between 1, 0 and 1 of y, which is 1 over 1 plus t, times dx by dt, which is 1 plus 2t dt. Okay, now unfortunately, if we bring those both together, we have got a top-heavy fraction. So we've got an improper algebraic fraction. So what we've actually got is between 0 and 1 of 1 plus 2t all over 1 plus t. So we've got to divide the top by the bottom. And if we divide 1 plus t into the top, I'll let you do that by yourself. I'm going to do it quite quickly. So we get area is in between 0 and 1, and that turns into 2 minus 1 over 1 plus t. So you can do algebraic long divisions needed there. And it's used quite a lot with these parametric ones. Right, we can hopefully start to integrate. So the area is going to be, that's going to give me 2t minus ln of 1 plus t, and that's in between 0 and 1. Put your limits in. We get 2 minus ln 2, and then we're going to get 0 minus ln 1, and that second part's just going to be 0, so we'll get 2 minus ln 2 is the area of our curve, our parametric one. Right, we come to do the volume now. We'll move on to the next page. So moving on to the volume, we have the volume is equal to the integral of pi y squared dx by dt. Right, so the volume is going to be pi in between 0 and 1 because we worked out the limits before. Y squared is 1 over 1 plus t all squared and multiplied by 1 plus 2t, so that's your dx by dt with respect to t. Right, what we have here then is a 1 plus 2t all over 1 plus t all squared, and this requires partial fractions. And it's partial fractions of the repeated root type, so it's going to be the same as a over 1 plus t all squared plus b over 1 plus t. Right, from that, I'm just going to do that really quickly. You can do that in more working just to make sure that you can do it. A is equal to minus 1 and b is equal to 2. So we get a volume between 0 and 1 of a, which is minus 1. I'm going to put it round in the other order, so I'm going to put 2 over 1 plus t minus 1 over 1 plus t all squared dt. Right, when we integrate that then, we get pi, and we get 2 ln 1 plus t. Take that to be 1 plus t to the minus 2 and add 1 to the index, divide through by the new index. So that's actually going to give me minus minus, so that gives me a plus 1 over 1 plus t, and that's in between 0 and 1. Put in your limits. Popping 1 in gives me 2 ln 2 plus a half for the first part, and then I'm going to get minus 2 ln 1 plus 1. So the volume altogether is going to be pi ln, sorry, 2 ln 2, and then a half minus 1 is going to give me minus a half. And that'd be a typical exam question, and these crop up quite often in C4. So I would recommend that you learn the formulae, especially this volume 1, because you're using your chain rule here, because we're changing from x with respect to x to with respect to t. Right, what I'd like you to do now then is looking at exercise 6i, question 1. If you can use Desmos, and it'll give you an idea what the graphs look like as well. And we want you to work out the area and the volume. The absolute minimum for you to do would be A, C and E, but it'd be quite useful for you to go on 3's an interesting question and so on. So again, absolute bare minimum to get some practice on that. The trig ones, the sec and the sec tan x might be a nice one to do as well, just to make sure that you can work in radians and with reciprocal functions as well. Right, that will take you a good 10 to 15 minutes, so come back when and check your answers for this one. So pause the video and then you can come back. Welcome back. And the solutions here, you can see your areas. Let's check your answer for A, B and C there for area and volume. Then if you'd done a little bit more, you can see there part D onwards. Question 2, if you'd given it a go, it was partial fractions and then some more integration. Some more parts of the question if you want to go on. As I said, that was the absolute bare minimum that I was asking you to do tail end of question 2, and then moving on to question 3. And then 4. This is the last part now of integration, and it's all about solving differential equations. You've done them before. We've done very, very simple ones in C2 when you've been given dy by dx and you had to work out what y was. That's the differential equation. What we have this time is we actually have x's and y's, and we have to separate variables. So it's taken the dx's with the f of x and the dy's with the g of y's, as you can see here. So what's happening is we've got dy by dx, we've got a function in x, we've got a function in y. If we take the y's to one side and the x's to the other side, we get two separate integrals, and then we can integrate and get back to where we started. So this is called separating the variables, and it brings together every technique that we've used in integration. Right, so let's try and separate these ones then. So we want to take the y's to one side and the x's to another if we can. So what's it going to look like? If I do dy by dx, it's equal to x tan y rather, all over 1 plus x squared. So I want to take the x's, leave them on the right hand side, and take the y onto the other side if we can. So just rearranging now, and we introduce the integral signs as well. So we've got the integral of 1 over tan y dy, so we'll leave the y's on the left hand side, and on the right hand side we've got x, 1 plus x squared, and dx. We'll change the tan y into cot, so that gives me cot y dy is equal to the integral of x 1 plus x squared dx. If you notice, x over 1 plus x squared, this is our sort of recognition. It's an f dash of x over an f of x. Now if we differentiated the bottom, we'd get 2x, so we've got to put a 2 in there and a half there. And that allows us to do the integral of the right hand side using natural log. So if we integrate cot, we get ln sine y, and that is equal to a half ln of 1 plus x squared plus c. So this is our by recognition. You could do it by substitution as well. You can do a little substitution at the side and work it out fully that way. So we've got a plus c happening there as well. We should be able to simplify this. So if we've got, I don't think there's anything. We can take the logs away of both sides, or we can change this. If we change this into ln k, we get ln sine y half ln. That would allow us to do our laws of logarithms. So we could say ln sine y is equal to a half now I'm going to take the half away actually, because the half's only with the 1 plus x squared, so it would be ln 1 plus x squared, the square root of the whole thing, plus ln k. And then I can bring them together using laws of logarithms. So it's very, very synoptic in this part. So ln of k square root of 1 plus x squared. And then we can just take away the natural logs. We've got single logs on each side, so that would allow us to put it in that form. The question will give you a good idea on what form to write it in if you need to simplify it a little bit further. So this is where we've got a general solution. So this is a family of solutions, and depending on what x, the values of x and y, we can work out a particular solution. So say we were given x is equal to 0 and y was equal to pi, say, then we could substitute those values in and get our constant k, because that's what's making it a general solution, is we've got this family of curves sine y equals, and that k is undefined. So remembering back to C2, you were given a point on the curve and that allowed you to get the actual original curve. So we can look at that in the next example, where we have boundary conditions. And these boundary conditions are really important because they allow you to find a particular solution. And that's what we're interested in, boundary conditions that give us a particular solution. That's really, really important. Right, so key thing here, particular solution of the differential equation. And how do I know it's going to be a particular equation? Solution rather, is because we've been given these boundary conditions. These are called boundary conditions. So it's just really certain values of x and y that will allow us to find out the actual equation for those particular values. Right, let's take our dy by dx then and see if we can rearrange that in terms of the x's on one side with dx and the y's on the other with dy. So, taking the dx's and the dy's across, we'll leave the minus 3 on the right hand side, so we'll get minus 3 and 2x plus 1, x plus 2, and we'll make that a dx. And then on the other side we're going to have 1 over y minus 2 dy. So I've just rearranged it and we get the two integrals on either side. Now, slight problem with the right hand side because we've got partial fractions, so we're going to have to use that technique to find out what those are. Right, so we've got minus 3, 2x plus 1 and x plus 2, and that's identical to a over 2x plus 1 and b over x plus 2. So we'll get minus 3 is identical to a times x plus 2 and b times 2x plus 1. We will let x equal minus 2, and that will give us minus 3b. So that tells me that b is equal to 1 and x is equal to minus a half. That gives me minus 3 is equal to 3 over 2a. So that tells me that a must be equal to minus 2. So we get the integral of 1 over y minus 2 with respect to y is the same as a. I'm going to change the order of these as well, so it's 1 over x plus 2 and minus 2 over 2x plus 1 dx. Right, this is where an integration comes in. So ln of y minus 2 is equal to ln of x plus 2 minus 2 ln of 2x plus 1, go back inside the bracket and divide through by 2, and then plus your constant of integration. And I'm actually going to change that into a natural log k so we can apply laws of logarithms, help us out. Right, so ln y minus 2 is equal to ln, these two cancel out, so we've got k times x plus 2 all over 2x plus 1, take the modulus of that, and then that allows us to take away the natural logs. So we've got y minus 2 is equal to k x plus 2 over 2x plus 1. And we've been given our boundary conditions. We've got x is equal to 1, y is equal to 4, and that will allow us to find out what k is. So put these values in, please, and come up with a value for k. So 4 minus 2 is equal to k, 1 plus 2 all over 2 plus 1. So that tells me that k must be equal to 2. Therefore, our particular solution, because we've got definite values of x and y, these boundary conditions, gives me 2 plus 2 x plus 2 all over 2x plus 1. So all I've done there is I've taken this one here, I've put 2 in there, I've taken the 2 across to the other side, and there's my particular solution. And if you really wanted to, you could multiply that out, and our final answer would be 3 plus 3 over 2x plus 1. And how has that happened? Well, as you can see, yet again, this is an improper algebraic fraction, so you would have to simplify that to get down to this part here. Questions to practice on these. If we turn to the next page, we have got exercise 6J. As an absolute bare minimum, I want you to do exercise 6J questions 1, the first column, and the second. Those are general solutions, and then what would be very, very useful is also to do 2 parts, 4A and 4D, to work out particular solutions. If you give yourself about 10-15 minutes to do those, pause the video and then come back to the solutions. And welcome back. And the solutions, if we look, questions that I asked you to do, I've put all of them on here. So if you wanted to try some more, then that's excellent, please do so. You can see you've got exponential in here as well, using laws of logarithms. So this is very, very synoptic. So check your answers here, please. So that's question 1. And moving on to the next page. Got question 2. Finishing off with 2. 2D is an interesting one because you've got quite a lot of trig in there and simplifying. Then we've got question 3. Didn't ask you to do that, but have a go at it. And then question 4, you were given boundary conditions, so that's allowing you to substitute values in. Remember, when you've got a trig, you must use radians. And then the rest of question 4 add those ones there. Okay, nearly there. We've got one last section and that's us finished completely on integration. And what we've got are differential equations that are in context, so it's a physical situation where we can solve using all the integration that we've done before. Example 25. The rate of increase, so remembering we've used that before when we've done rate, and that denotes dt, doesn't it, by dt. The increase in population of microorganisms at time t is given by dp by dt is equal to kp. K is a positive constant, so remember that when we're working it out towards the end. Given that t is equal to 0, so these are called the initial conditions, so usually at initial conditions t is equal to 0, some other things will be equal to 0 as well. The population was of size 8, so p was equal to 8. So from that situation there, t is equal to 0 and p is equal to 8. I can write down those two things. So that's like boundary conditions that will allow me to find out my constant. And at t equals 1, the population is 56. So there's another set of boundary conditions. And then we're asked to find the size of the population at time t equals 0. So we've got a differential equation. We've got dp by dt, and it's equal to kp. And to solve that, we need to separate the variables. So we need 1 over p for dp, and we'll leave the k where it is for dt. If we integrate both sides, we get natural log of p is equal to kt plus a constant. Now if you notice, what we've actually got here is a constant with the differential equation, but we've got a constant of integration. So that's why we were given two boundary conditions, because that will allow us to find out k and c. So, two unknowns, two lots of boundary conditions, we can actually pop t equals 0 in. So when t is equal to 0, p is equal to 8. If we put that in, we get ln ln 8 is equal to, t is equal to 0, so it's 0 plus c. So that tells me that c must be equal to natural log of 8. Now if we go back, we get ln p is equal to kt plus ln 8. We're now given other conditions, and those other conditions were t is equal to 1 and p is equal to 56. Then that allows us to substitute in here, and we'll get ln 56 is equal to k plus ln 8. So k is equal to ln 56 minus ln 8. So k, if we use our laws of logarithms, 56 over 8, so it's equal to, so it'll give us ln 7. So we now have our equation. So we'll find out what k is and what c is. So going back to the beginning, we have ln p is equal to k, which was t times ln 7, and c, which was ln 8. And if we now put in the question, if we go back, it says find the population at time equals t equals 2. So at t equals 2, ln p is equal to 2 natural log of 7 plus natural log of 8 and let's work this out. So ln p is equal to ln of 49 times 8. So ln p is equal to ln 392. If we just take the logs away, so p is equal to 392. So you can see that there are lots and lots of synoptic elements in terms of your laws of logarithms. Okay, this is the absolute last exercise we're looking at, which is exercise 6k, and I'd like you to do all 4 questions. It should take you a little while. Pause the video again, and from there we will look at the questions. And welcome back, and here are the solutions. Question 1 and 2. Check your solutions. And then moving on, question 3. And then question 4. Right, so that's a completely finished integration, and what I would like you to do for homework are these C4 questions, and as you can see, if you can hand these in on Tuesday, then that's us completely finished, and then next week we will do some exam practice, exam papers, and you should now be revising for your mock exams for the week commencing the 27th of March.